for what we did yesterday real quick. So I want to show you a nifty example, let me start with the real basics. If I say A is 2, 3, 1, negative 1, 4, 0. B is negative 1, 5, bless you, 6, 1, 2. What would A minus 2B be? Alright, how'd you get 0?
So 2 times negative 1 would be negative 2, and 2 minus negative 2. So
4. So maybe a good idea would be, here's A. Now here's what I do. Bless you. Here's what I do. I make this plus negative 2 times B just to make it easier, because minus and negative can easily screw us up, right? You guys kind of with me on what I'm doing here? This is A. Alright, that's A. Plus negative 2B. Plus, what's negative 2B? 2. Negative 10. Negative 4. Negative 12. Negative 2. Negative 4. Right, I mean, so scalar multiplication, addition, subtraction, all that kind of stuff with matrices are very easy. Why was I able to subtract these? Or why was I able to combine these in the first place? They're both what? 2 by 3s. I like it. Cool. So now I can put these together. So I get
0.
Oh, he wants to be like, make it 0, come on. It wants to be 0, Jeff. What are you doing? Poor number. They have no self-determination. Negative 13. 2. Negative 4. Yeah. Okay, simple. Easy. Adding, subtracting numbers. Yeah. Alright. So all that stuff should be easy. No problem. Bless you. Of course, coming off of that, can I do this? How big is A? 2 by 3. How big is B? 2 by 3. No. Shit. Right? So if you weren't here yesterday, the inner numbers have to match because of the way that we define matrix multiplication. I haven't told you why we define it that way, but I will. So let's remember how to do it. Let's give ourselves Let's give ourselves some grammar lessons, and then we'll give ourselves 2 more little tiny. I'm doing this on purpose here, as I do most of what I do. This is really neat. You ready? Is D the 1 matrix? The 1. It's D-O. No? Alright. I like that one. You got it? Alright. No, you got it, but it wasn't funny. So this is not quite 1, right? What's wrong? Why is this not quite 1? They're in the wrong place, right? You can either say the rows switched, or you can even say the columns switched. Very interesting. Remember what we just said, right? Because the 1 matrix would be 1, 0, 0, 1. Okay, cool. Alright, now watch this. You ready? This is kind of cool. If I do D times C, and of course I can because they're both 2 by 2. All the 2's everywhere, so 2's in the middle match, and the answer is going to be 2 by 2. The outside ones tell you how big it's going to be. Remember that? 2 by 2, 2 by 2. These match, good. These tell you how big the answer is going to be, right? So this would be 0, 1, 1, 0 times 2, negative 1, 3, 5. This will be a reminder of how this works, plus finally an indication of why we did this as we did. Why we defined matrix multiplication the way we did. How do you multiply this? Yeah, 0, 1. So 0 times 2 plus 1 times 3. It's crazy. 0 times negative 1 plus 1 times 5. 1 times 2 plus 0. 1 times negative 1 plus 0. What did multiplying this by this do to this? Switch the rows. Do you see that? Do you see that? Do you see that? Can you see? All right. Now, so you guys take a second and do C times D. If you didn't pick this up from yesterday, matrix multiplication is not commutative. You understand? C times D is not necessarily equal to D times C. In fact, sometimes it'll work one way and it won't work the other. I should be quick. Either you know it and it's quick, or you don't know it and that's even quicker. So what do you get here? Yeah, 0 minus 1. 2 plus 0. 0 plus 5. 3 plus 0. Get out of there, weird thing. So what happened to this? What happened to this? The column switch, kick ass. So multiplying by this in front makes the row switch. And in fact, this is how far away from the 1 matrix the rows are switched. But if we multiply on the other side, what happened is the column switched. Because how close is this to the 1 matrix? It's a column switch away, right? So what matrices are, they're almost like commands. It's almost like a computer program. You're attacking it. What this is really called, we're not going to get totally into this. This is called an operator. Operator. This is in the matrix. Also. Anyway, so, right, it's really cool. There's a whole class of things called operators. And very often, sometimes there are things that we know already, and we just kind of recast them and say it's an operator. But sometimes operators are just operators. This operates on this and makes it do this. That's a wider classification than functions, because they can do more than functions can do. All right? How much you have to understand that? Not much. But I really want you to understand, that's why we define matrix multiplication the way we do, because we want matrices to do more shit than they already can do. We want them to live for a reason. Right? If I just define multiplication to be 2 times 0, and then it's a bunch of numbers I'm multiplying, there's nothing new, why would we do that shit? We wouldn't do that shit. Math people, we got stuff going on. We want to do something that actually gets us somewhere. I don't know if you guys remember. Let me give you one more example. And let me give you a larger problem. Alright, so multiply these. Oh yeah, let's do this. Let me see. Yeah. First off, can you do it? Are you allowed to do it? How big is this?
32.
3 by 3, and this is 3 by 2, right? 3 by 2. So can you do it? Yes, check. The inner ones match, and the answer is going to be 3 by 2, just as big as this dude. I like it. Which, if you really think about it, makes sense. If this guy is operating on this guy, it's got to be the same size as it was. It's just going to change. The inside is going to change, right? Alright, so it should be relatively quick. There's a lot of zeros in there, so if you understand how this works, it should be pretty quick. Alright, so how do I get the first? So it's going to be a 3 by 2. How do I get this guy? The first dude. Yeah, 1 times 2, 0, 0. 1 times 5, 0, 0. Alright. I mean, this makes sense because this first guy says the first row stays the same. Does that kind of make sense? And how much you have to understand? Not much, but I really want to kind of, especially because I think a decent number you had to go to linear algebra, you're going to be getting into this really deep. Operators and shit. Oh yeah. We're not going to get that deep into it. How's the next one work here? Let's see. 0, 3 minus 1, 2, 0, 4 plus 2, 6. So where'd 2 and 2, 6 come from, really? 2, 6 came from this plus this, right? And look what this says. It says, again, I'm going a little bit beyond. Here's what 1 looks like, right? You with me? How do I make this show up? Well, what I do, what rows would I add together to make this happen? Row 2 and 3. And how did we get 2, 6? We added row 2 and 3. So this is like a command. This is like a computer program almost. It's really, really neat. Now, the minute I start putting all kinds of shit all over the place, it's not so easy to tease out. If I made this 7, 8, negative 4, 6, 3, you're not going to go, oh yeah, it's going to do this. No, you just do the multiplication. I can't see what it's doing. Now, what is this last row going to do? How do I get 1, 0, 1? The first row plus the last row, right? That would get 1, 0, 1. So sure enough, when I do this, I get 2 plus nothing minus 1. So 2 minus 1. And 5 plus 2. Nifty. Alright, well, let me step away from that for a minute. Let me step away from operators and all that kind of stuff. Let's just do a straight up multiplication. I want to make sure everybody's on board with how multiplication works. It's completely new to anything we've done before, really. But once you see how it works, you got it. The minute it's in, it's in. So say if I had a 2 by 3, could I multiply that by a 3 by 1?
Yes.
Yes. All right, so let's make a 2 by 3. So there'll be a 2 by 3. So it doesn't matter. 5, negative 1. 2, 3, 4, negative 2. Sure. And then a 3 by 1. Negative 2, 3, and 1. So how big is the answer going to be? The insides match, check. The outside one, so I know it's going to be 2 by 1. That's awesome. A little tiny dude, right? Alright. So then you get what? You get negative 10. Minus 3 is negative 13. Plus 2. Negative 11, cool. Let me stop there. So everybody see where that negative 11 came from. If you were here yesterday, hopefully that whole thing made sense. If you weren't, does it make sense? You see where it came from, right? Hopefully you understand a little bit better why we define multiplication this way. If we defined it the way that addition's defined, that would be shit. There would be no reason for matrices. Why would we need them? Yes?
So what you just did was 5 times -2 plus -1 times 3 plus 2 times 1.
Good. And that's why in the little handout I call it distribution.
Okay.
It's sort of like distribution, isn't it? Cool. I like it. And so what about the next one? Yeah, -6 plus 12 is 6 minus 2 is 4. So if you had a 20 by a 1 by 20 matrix times a 20 by 1 matrix, how big would the answer be? 1 by 1. It'd be one number. It's awesome.
And if it's irregular, you just repeat it and then multiply it by 0, the extra one by 0? Or
Extra one, how do you mean? Now here's the thing. Here's the big thing. Why was I able to multiply these? These matched. And you see why, because I need this whole row of numbers to go with a column of numbers. Every number has to have another number to go with. So if I try to multiply 2 by 3 times a 2 by 1, would that work? No. And if I did this, let me just take the one I've got over there real quick. Got it, Jeff. And then I do a 2 by 1. So we'll just do 5, 7. If I try to start doing this, I'll go 25 minus 7. It's not a 0 here. If it was a 0 here, then it would exist there. It exists. But there's not even a blank spot here. This is the weird shit we did yesterday, right? We just went off the deep edge for a little while and said, what would things be like if there wasn't even nothing there? Not even nothing. There's not a space for nothing. It's just not any, it's not. It's not. That's the name of it. It's the not. Right? Or maybe it's from like Never-Ending Story. They look like such strong hands. There you go. Alright, good. I like my references. I don't care. Alright, does that make sense? I think that's what you're asking, right? You don't assume there's a 0 there because there's not even a place for a 0 to even be assumed. There's not a place. Free. Alright. Cool. So, once you get matrix multiplication down, it doesn't matter how big or small it is, it's the same thing every time. It's relatively quick. Okay? So, the only other thing I wanted to do today, I'm going to give us a very nice short day. I knew you'd be excited about that. I think, let me find it real quick. Where do they have it in here? Shoot. It's not here, that's right.
does division work the same way?
Here, alright. Oh, I like that. Good. Beautiful question. Division. And actually that gets right into the next section. Division of matrices does not exist. You cannot divide two matrices. What you do instead... If I told you that multiplication exists and division doesn't, and you had to solve this equation, multiplication exists, but division does not.
Like what?
Multiply by other, you still multiply, right? So you could say that 1/2 is a number. You don't have to think of that as a division bar, right? And what is 1/2 related to 2? It's reciprocal. What's the other name for it? It's the inverse. Kick ass. So in matrices, we can't do division of matrices. What we do is we multiply by the matrices. I like that. It's an awesome thing I just did. The matrices inverse. I like it. And think about it. If a matrix is fundamentally a group of operations, a group of commands, you go this way. You 2 times you go add to this guy. That's what it is. Then I can't divide by commands. I can apply the opposite commands, right? Does that make sense? Come on. What? No, that's horrible. That would be horrible if that was the way I taught. Does it make sense? Don't say no. It's like, okay, it makes sense. My students understand everything.
How would you write it?
All right, so here's how we gotta do it. I want to take, now watch this, it's kind of nifty. If I take, watch this. I don't even know if this has an answer, so we're not going to actually solve this, but I just want to give you, yeah. All right. Now we know how to set this up as its own augmented matrix that represents this. I want to set up right now something different. I want to set up a matrix equation. A matrix equation would be A times X equals B, where this is a matrix. This is a matrix, but it's a something by one matrix. In this case, it'd be a 3 by 1. So that's very often called a vector. This doesn't really matter. So a vector is just a matrix where one dimension is 1. So this is like a little tiny matrix, which is called a vector. Yeah, a vector. And then this is the answer matrix. It's going to have all the answers in it, right? Or answer vector, if you want. Okay. So now watch this. It's kind of neat. What A is going to be the collection of coefficients, like it always was. I'm not going to augment it. I'm not going to put the line there. I'm going to have the answers on the other side. So it's not like me making this and just putting a line here. I'm actually going to have a matrix that collects all the coefficients, and on the other side is going to be this. So this is easy. This side will be that. Woo! Now what's the matrix A? What's the coefficients? Yeah, 2, 5, 6, 7, negative 1, negative 3, 4, 3, 5, 1. You guys with me? All right, now watch this. It's kind of cool. What would I multiply 2 by to get this? 2 times what is 2x? 2 times 1 is 2. 2 times what is 2x? X. It's crazy. And then 5 times. Do you see how? So this is my variable vector, right? Or variable matrix. It's fine if you don't want to say vector. Do you see how, if I work this out, do I not get this back? If I work this out, if I multiply this out, what do I get? Plus 5y minus 7z equals 4. Then the second, negative 1x minus 3y plus 4z equals 1. Yes, sir?
Will the vector always be like the letters?
No. This is a vector also. So a vector is just a matrix where one dimension is 1. So 7 by 1 matrix, you can look at it as a 7-component vector.
Okay.
How important is all that? Not horribly, but that's how we look at vectors and matrices. That's their connection.
But when you have a variable and you're trying to make an equation, will the variable vector have like the variables in it only?
Yes.
Okay.
It has to, yes. And that's why we call that bad boy variable vector. And that's why, in reality, if you look in the book, this should be bolded. And normally in the board, I would put what's a vector symbol over that, but we're not getting all that deep into this anyway, so it doesn't really matter. So in order to solve this, in order to be able to solve this, what I would have to do is I'd have to figure out what A inverse is. Because if I multiply this side by A inverse, what would happen? These would cancel, I have x. So if I multiply by A inverse, I better multiply this by A inverse. Now what's nifty is, I want you to realize something. This is not the same as putting A inverse on that side. I have to have that on the same side. Because remember, it's not commutative. Shit. So when you multiply one side by a matrix, the other side you have to multiply on the same side of that other side. So here I multiplied in front. There I better multiply in front. Okay. Weird little thing about matrices. Just because they're not commutative. Right? So does that idea make sense? That's what we've been doing ever since you first learned how to solve equations. You've been applying the inverse operation to both sides. Yeah.
Must it be multiplied from the front, or if you said multiply from the back?
Now watch. All right, I like it. So here's my equation, right? Can I turn these around? No. Because A times X is not the same as X times A. And in fact, here's a good example. How big is this? How big is this? 3 by 1. If I turn them around, will it work still? No, because then it'd be a 1 and a 3 in the middle. Shit. You see that? So I cannot turn these around. You still don't believe me, but I'm not sure what more to do. If I did try to turn them around. Now, if I turn them around, what would I have to do with this? Is that what you're thinking? I'd have to turn this like that, and I'd have to move this. I'd have to do a lot of rotating. So it's not impossible, but I cannot just pick them up and move them. You with me? I'd have to do a lot of other shit to make that work. So, if I have it like this, and I try to multiply this side, can this go here? No, I can't jump over that. Because again, it's not commutative. So if I want to kill the A, I have to attack the A directly. I have to do it there. I have to multiply on that side. It's so weird to us. Because we're so used to, if I got a 7x and a 1/7, well, that's freaking x, right? Because we have commutativity. We don't even move them, we just do it without thinking about it. But we don't have commutativity here. If you want that to be with this guy, you better put it with him right at the beginning. Because you put it over there, there's no way he's getting over there. There's no way. You just can't. They don't commute. So on this side, you have to do it also, bam, in the front. All right, cool. So I'll tell you this. Section 10.5 is all about finding inverses. And that's what we're going to focus on next time. That's enough for today. I'll give you guys a nice little break. We've done enough stuff here the past few days. Think you'll agree? Oh, okay. Who else needs their quiz? Hey, do you need your quiz? Sucks for me, because I don't have a quiz. Why don't I have a quiz? Wait, you're Alexander. Okay, good. Oh, that's fine. Sure.
Do you have enough copy of the quiz?
Yes.
Just so I can like.
Yeah. Sure. Because it's an operator, you can think of it having like that.